Here's the answer for example 2. It's a long one. The initial concentrations, I'll have 5 moles per liter for my hydrogen, 4 moles per liter for my iodine, and because it's not mentioned, I'm going to assume that I start off with 0 moles per liter of HI. I recommended making HI's concentration at equilibrium 2x. That makes its change a positive 2x. This works very well because when I move to iodine, I have a 1 to 2 mole ratio. That means that I2 will change by a minus x, and I avoid having fractions in my ice table. Because I have a 1 to 1 mole ratio here, the hydrogen will also go down by x, giving me an equilibrium concentration of 5 minus x. When you write the equilibrium expression, don't forget to raise the concentration of the HI by 2. You have a 2 coefficient here. My question tells me that that equals 20. Now unfortunately, when I sub in my numbers, I don't have a perfect square. My first hint is because the brackets in the denominator are not the same. So this means I can't use my first trick and take the square root of both sides. I have to follow through, expand out, and use quadratic formula. A common mistake people make is when expanding this. They would just change this into 2x squared. You have to square the 2 and square the x. So this equals 4x squared. Using distributive law, I would times the 5 by 4, which gives me 20. I would get a minus 5x and a minus 4x to give me a minus 9x and a plus x squared. I would then take this bracket and move it over to this side to get it out of the denominator. I would then have to expand my 20 over the 3 terms using distributive law. In order to use quadratic formula, I need this in the ax squared plus bx plus c form. So I'm going to subtract 4x squared so that I get 0 on this side. Then I can sub it into quadratic formula. Remember, quadratics always give you 2 answers. If I add 82 to my 180, I get an answer of 8.20. If I subtract the 82, I get an answer of 3.05. Now only one answer will be correct. If you have a look at your ice table again, the 8.2 doesn't make any sense at all. I defined the concentration of I2 as being 4 minus x. Well, if x equals 8.2, then I will have negative chemicals. That does not exist. So therefore, x equals 3.05. I can then take the 3.05 and sub it back into my ice table. The concentration of the hydrogen I defined as being 5 minus x. So that is 1.95 moles per liter. The concentration of the I2 is 4 minus x, so 0.95 moles per liter. And the concentration of the HI is 2 times x, which equals 6.10 moles per liter. Example 3 introduces a new trick to avoid doing quadratic formula. I don't particularly enjoy doing them, so I try to avoid them whenever I can. In this question, I have an initial concentration of 0.085 for my nitrogen, 0.038 for my oxygen, and NO is not mentioned, so I'm going to assume that it's going to start off as 0 moles per liter. Because I have a 2 here, I'm going to define the concentration at equilibrium as being 2x for my nitrogen monoxide. That gives me a change of plus 2x, and I fill in the rest of my ice table using mole ratios. My Kc expression is going to be the concentration of NO squared divided by nitrogen and oxygen, and it tells me in the question that this equals 4.2 times 10 to the minus 8. Now, looking at this Kc value tells you something about what your answer is going to be. It's 10 to the minus 8. This is incredibly small. This means that the forward reaction very rarely happens. It does occur because the Kc value is bigger than 10 to the minus 10, but it means we're going to have very little NO in our system. So let's see if the amount of NO is going to be significant. Here's the test as described by the box on the right-hand side of your page. If K is really small, see if the lowest initial concentration divided by your constant is bigger than 500. If it is, it means that X is so small that the initial concentration minus the X will be the initial concentration, following Sigdig rules. That means we can ignore the minus X's in our equilibrium concentration of our reactants. Let's check out and see if it works. If you take our lowest initial concentration, 0.038, and divide it by our constant, it is significantly larger than 500, so our assumption works. That means when I sub into my Kc expression, I'm going to sub in a 2x and just a 0.085 and a 0.038. If the change in concentration is going to be so small, it doesn't affect the concentration of the oxygen. Because it's larger, it's also not going to affect the concentration of the nitrogen. Now I've simplified my math and I can avoid doing a quadratic formula. Now let's simplify the math. This here becomes a 4x squared, and I can times these two together and times it by that to get rid of my denominator. If I divide both sides by 4 and then take the square root of both sides, I will solve for x. Now, let's find out our equilibrium concentrations. If I take 0.085 and subtract it from x, I get 0.085 if I keep 2 sigdigs. So that means the assumption works. X is so small, it doesn't affect the concentration of my reactants with sigdigs taken into account. The same thing is true for my oxygen concentration. The concentration of NO I define as being 2x, so that equals 1.2 times 10 to the minus 5 moles per liter. Now you don't have to use this assumption trick. You are more than welcome to expand everything out and sub it into quadratic formula. It just becomes harder math, more work, and more chances to make mistakes.